Today, we're going to continue our discussion of the analysis of variance and talk about the repeated measures analysis of variance. We've talked about the one-way between groups and factorial between groups, which are both basically extensions of the independent samples t-test, where we have independent groups that we're comparing. So today we're going to talk about extending the dependent samples t-test, where we're comparing the same people across time or matched pairs of people. We're going to now extend that to more than 2 time points or more than 2 paired groups, which I guess is possible, but not as likely. But so before we talked about sort of pre versus post testing with the intervention in between, now we're going to talk about extending that out to having maybe pre-post and a follow-up or something like that, where you have 3 different time points or 4 time points or 5. You can think about looking at something like, math scores across 9th, 10th, 11th, 12th grades or something like that. That would be a repeated measures version of something like an ANOVA. That's what we're talking about today. How do we actually extend that out and use what we know about the data, the fact that they're related, or they're the same people being measured multiple times, to our advantage, so we can actually look at, is there a meaningful difference across time? All right. So we're going to, go a little deeper into like what is or what makes or what are repeated measures. We're going to go through an example, of course, and we're going to talk about the assumptions of repeated measures ANOVA. We're going to talk about some advantages versus disadvantages of doing a repeated measures ANOVA versus one of the between groups or independent samples versions. And then we'll talk about effect size once again when it comes to ANOVA. I do this joking at the corner, which is funny that you read it. It's a biologist, a chemist, and a statistician are out hunting. The biologist shoots at a deer and misses 5 feet to the left. The chemist takes a shot and misses 5 feet to the right. The statistician yells, "We got him!" The idea that we sort of measure accuracy not at being perfectly accurate, like being able to shoot the deer, but the fact that we take measures like the mean or something like that that we know are going to vary from time to time, and we think of a measure like the mean to be a good measure if it is off an equal amount both above and below the target mean that we're looking for. So that's why statisticians want to see sort of shooting 5 feet to the right and shooting 5 feet to the left as being good, because we're sort of equally going above and below the target. This means we're sort of, at least in some way, accurately capturing the mean, which is why they say we got them. I know jokes aren't as funny when you got to explain them, but still, just in case you didn't quite get the joke, that's where it's coming from. All right, let's move on. Speaking of repeated measures, this quote, which I think is often, I've seen it, I've seen it tied to many different people, including Einstein and other people. So I don't know who actually said it, so I sort of left it as unknown. But insanity is doing the same thing over and over again and expecting different results. So a repeated measures ANOVA sort of reminds me, or at least makes me think of this quote somewhat. So with between subject designs, different subjects serve in different treatment levels, different conditions. We have an IV like, we talked about the Grand Theft Auto versus Lego game. We talked about the different baby foods, right? There were different groups of babies that were randomly assigned to different conditions. There are different people assigned to play the different video games. So there's random assignment. There are different independent groups of subjects assigned to conditions. That's what we've already covered. Repeated measures designs, each subject receives all levels of at least one of the independent variables. Now I say at least one because there is a kind of design called a mixed ANOVA in which there are both between and repeated measures components. We're not going to talk about that, or we're not going to go into those. We don't have the time to cover that in this course, but they do exist. So to have a repeated measures component in your design means that each subject repeats or receives all the levels of at least one of those independent variables. And that's what we're going to talk about today. So we're not talking about the mixed ANOVA, where there's a blend of between and within. We're talking about just repeated measures. All right, so something that's completely repeated without any between groups. All right. So all subjects get all treatments. All subjects receive all levels of the independent variable. Different n's are unusual. So when we talk about unequal n, usually it's just that a different number of subjects are assigned to different levels of an IV. Here, that's not quite the same. So different n's, just having different n's assigned to conditions, it's not really possible. What is possible is something called dropout, or oftentimes referred to as mortality, where people start off at time 1 and then they don't show up again at time 2 or time 3. They sort of drop out of the study. So those kinds of unequal n are more common. But just having, but we usually think of that as dropout, not unequal n. But we're going to take the simplest case and look at just examples. The example we're going to go through, where everyone sort of was in all conditions without any dropout, because dealing with dropout and so subject mortality is a whole other issue. Like, how do you deal with that? There's intent to treat approaches. There's data imputation, there's all kinds of things, and it goes sort of above and beyond the topics of this course. So we're going to stick to the simplest case, where we're going to look at the complete cases, where people start off at time 1, they show up again at time 2, they show up again at time 3, and they're sort of there through the whole thing. And treatments are usually carried out serially, like they're in a series, like one after another. So it's usually done so you got time 1 versus time 2 versus time 3. There are repeated measures designs where you're sort of looking at measures at the same time but on the same subject, which is another form of repeated measures. Like if you're looking at, let's say, an EEG, where you have different measures, different electrodes in different parts of the brain, they're all being measured simultaneously. So they're not being measured in serial, but it can be looked at as a repeated measures design, because all those things are being measured at the same time on the same subject. So it is within the same subject. But the example we're going to go through today is just, again, one where it's done in series, time 1, time 2, time 3. But that's not the only kind of repeated measure design you could find. So let's take our repeated measures design, repeated measures t-test we did before, and let's extend it out a little bit. So if you recall, we talked about looking at THC and memory, and we did a pre-post test where participants did a pre-test memory recall. They ate some Rice Krispies treats, pictured there in green, that contained THC, and then they came back and did a second recall afterwards to see if THC sort of impacted their memory. So let's extend it out. So we know, at least from our sort of simulated example from before, we saw that memory was impacted, so pre to post. So if we want to look at that, extend it out a little bit, so we could look at it beyond just the pre-post and see if memory does start to come back around. So one way to think about this is, if people have a memory task and then they have THC in the system, the THC actually impairs their memory, but how long does that last, and is there sort of a more permanent or long-lasting effect of THC on memory? So we can do that by adding in another task, another portion of it that looks at the sort of more long-term effect. So this is the data from before. Pre versus post, we saw that there was a drop in the number of words recalled. All right, so that's what we did before. Data is the same as it was before. So what we want to know now is, what if we want to know if that effect persists? So there is pre and post, and I think there was, if I remember quickly, let's go back here for a second. Yeah, so there's a 2-hour window in between the pre and the post, and that was to allow them to digest the the Rice Krispies somewhat, right? Because it's not like an immediate effect. They actually have to digest it. The THC's got to get in their system. So there was 2 hours in between. So the no THC, they ate the Rice Krispies treats, and then they were to take a recall task again at post, and there was like a 2-hour window in between the two of them. Okay. So I remember the question is, does THC impact memory? So in the short term, we showed that there was some impact, right? So again, this is simulated; it's not real data, but this does sort of mimic some other studies that have shown, at least in the short term, it does. So what if we then came back after 6 hours and did the task again? We have a new list of 50 words. We give them a distractor task, and then we have them do a recall task again. So it's now the third time they've done a recall task. So now we have 150 different words, right? The first list of 50, the second list of 50, and now we're at a third list of 50 words, and we're having them sort of do a recall task there. Now, what you expect is, if it's really THC that's having the impact, and it's only when it's in their system, there should be sort of a rebound effect, right? Their memory, their recall should come back after the THC's had some time. Now, it's 6 hours. I actually don't know how long THC lasts in your system. Maybe it's longer than 6 hours. I mean, this is not realistic. But let's assume, for anybody watching this, that either knows, via research or through their own personal experience, that 6 hours isn't long enough. Let's just assume it is. That after 6 hours, the THCs sort of move through your system to see if memory, if the recall does come back. Okay. So now we have what I'm calling pre, post, and follow-up. So the pre is, again, before ingesting THC. The post is 2 hours after ingesting THC. And then the follow-up is 6 hours after that to see if their ability to recall these words, their memory, short-term memory, starts to come back, starts to rebound. So how do we account for repeated measures? So we have participant 1 now has not only a pre and a post score, they have a follow-up score. And you see there is a bit of, right, pre, and then they drop the post, and they come back at follow-up. Right, pre is high, they drop a post, they come back up. Right, so it's not perfect. Not everybody does exactly the same. Like this person, number 9, they dropped to 7 and then stayed at 7. This person, number 8, started at 8, went up to 14. They went exactly the opposite, direction, the trend, and then sort of then went back down again. So not everyone's perfectly following the same pattern, but there is a general pattern that 17.5 at pre. At post, they drop down to 13.9, and then they do come back up. Now, this could be because, like I said, maybe 6 hours isn't long enough. Maybe there's still some residual THC in their system, so they haven't fully rebounded yet. But maybe there's also some longer lasting effects. Maybe everyone is just tired now after having THC in their system, or who knows. You can go with the stereotype. Everyone's too distracted with the munchies or something to concentrate on the recall of the words. I don't know. But the main question here is, regardless of what we're measuring in terms of memory and stuff, we now have 3 different scores for every single person. So how do we do that? How do we approach it? So when we talked about this with between groups, we could do 3 dependent samples t-tests, right? I could actually create different scores. I can create a different score for, say, I don't know, post minus pre, right? I can have one of those. I can do a t-test for that. I can have another different score for, I'll just call it FU, it's kind of funny. Follow-up minus post, all right? I can do another dependent samples. Let me find the difference for follow-up minus pre. I'm going to have 3 different dependent samples t-tests. But as we've seen with the independent samples test, they're doing multiple t-tests, right? Each time, this has got a 0.05 type 1 error. This one's also got a 0.05 type 1 error. So there's that one. The more tests we do, the more likely we are to make type 1 errors, because we're sort of adding more and more chances of doing so. So that's not going to be the way. We're not going to do that. So what allowed us to do this, and this approach made sense, the dependent samples, because it's the same person number one, these are the same person's scores, it makes sense to subtract them. Right? Subtracting scores from the same person makes sense, which is why we could handle the dependent samples t-test differently than an independent samples t-test, because they're the same person. Right? With independent samples, it doesn't make sense to subtract individual scores. But with dependent samples or repeated measures, it does. Now, I don't want to do that. I don't want to take and create, 3 different scores across these things. So what else could I do? How else could I handle this? How else can I address this without having to take differences? Well, one thing that's unique about repeated measures, so not only can we subtract scores because they're from the same person, but as soon as I have more than a couple scores from any one source, I can take an average. I can take, person number one, their pre-test score plus their post-test score plus their follow-up score. I can divide by 3 and I can get an average recall for person number one. I can get an average recall for person number 2. I can get a bunch of participant means, which up to this point sounds like a strange thing. We don't usually take averages for participants because that's odd. We usually are averaging the groups. So I want an average for pre, an average for post. I want an average for, Gerber, an average for BeechNut, because I want to compare those averages. Well, that's because in those examples, each person only contributed 1 score. There was only 1 contribution from each person, so it doesn't make any sense to take an average of their scores. Well, now I have 3 scores from the same person, so it starts to make a little more sense. I actually can average out their scores, and I can start to see if there's just people in general that have higher, like look at this person has just higher recall in general, right? They just are recalling more words regardless of what the condition is, right? This person down here, regardless of whether THC is in their system or not, they're not very good at recall. Right? Recall is not their thing. So we can start to see that there's general patterns to people's scoring, and we can start to use that to our advantage. So let's talk about that. How do we do that? I mean, doing it's the easy part, but how do we use that to our advantage is the part that is the new step, new thing. So just like I mentioned a second ago in the last slide, that we can actually take and create subject means, right? So that part's easy. 15 plus 13 plus 16 divided by 3, I get that subject 1's average is 14.667. And what you can start to see is, again, if you ignore THC for a second, you just start to see which people have, on average, sort of better or worse recall, right? So these are starting to look like some individual differences, right? So this part is almost seems, not directly, related to THC or not THC. It's just these people just have better or worse recall in general. So we can sort of look at this as sort of the individual differences or the random error around sort of memory. And we can use that to sort of figure out, all right, well, how much are subjects sort of just varying consistently across time, and use that to our advantage. Now, one of the reasons why this becomes important is because in an independent samples t-test, we calculate the sum of squares within groups, right? So it's the average of, if I take and square this and square that and square that, I can get their variances. I'm essentially getting an average of the within groups variance. So we use in a between groups, or an independent samples version, right? We use sum of squares within groups, which are, well, really, I guess, mean square within groups, right? The sum of squares and mean squares within groups are what we use as our error term in F. Right? So when we go to create an F value, we use the mean square within groups. Okay, and we do this because we consider this to be sort of random noise. So this is random variability, right? So if these are three different sets of people, how much they vary in this group versus how much they vary here, how much they vary there. We average that out and say, okay, where this is our measure of sort of random variability that we're going to use as our error term. We're going to divide our F value, or divide our mean square between groups by this to get our F value, because we consider this to be random. It's random between subject variability. Well, the problem here is that in a repeated measures version of this, it doesn't work, because this mean square within groups, right, the variability here versus variability there versus variability there, well, there's some certain amount of consistency, which we can see in the subject means. Right, this subject is relatively high versus everybody else. This subject's relatively the lowest. Right, so there's some consistent ranking or scoring by subjects across time. And if something is consistent, it's not random. So my MS within groups is no longer totally random. I still can't tell you why this subject is higher and this subject's always sort of lower. I don't know why, but it's not completely random anymore. So I can't just use MS within groups to be my error anymore. So repeated measures, I need a different measure of error. I need to figure out some other way to look at error that hones in on what is really the random part. What's really random in this? Right? How do we get at randomness when and account for the fact that there's some consistent scoring across time, be able to remove that to get some kind of error term for our F that really is random. It can't be MS within groups anymore, because that's got consistency between subjects across time. So this isn't fully random anymore. There's some random and some non-random components. So this is not going to be the error term we're going to use. We're going to have to figure out some other error that is the random part of all this. And that's what makes a repeated measures version of ANOVA different than the between groups version. Down here, this 15.767 is still the grand mean. I can take the average of these subject means and I'll get 15.767. And take the average of these different time means, pre, post, follow-up, I'll get 15.767. I can take the average of all of these 30 scores and I'll also get 15.767. So this is sort of the grand mean here. And this 4.680 is the standard deviation of these scores. This is how much the subject scores actually vary or deviate from one another around that grand mean. I don't know why I wrote S so strange there. All right, so we need to figure out a way to split up mean square within groups. I need to figure out a way to find the random piece to that and use it here and remove the part that's consistent, that relates to subject differences here, because if it's consistent, it's not random. So we need to be able to identify that and pull it out. And that's going to be the process we're going to go through for this one-way repeated measures ANOVA. So some preliminary observations of the data on the previous slide is that subjects differ from each other, right? There is some subject differences, especially along those averages. So we're getting some between subjects variability. And you also notice that the means decrease at first and then increase. So we're getting this sort of like there's a drop in recall and then a rebound in recall that we would expect if it's the THC in their system that's causing the memory impairment. Once the THC is out, you expect it then to the memory to come back. In repeated measures ANOVA in the analysis, we're still going to deal, there's a lot of things. So the good news, right, we up here, you can make it, you know, the good news is looking at things like total and between groups stays the same. Right? That's the huge good news. And actually, even the sum of scores within groups is the same. So we're still going to deal with those things. We're just going to have to deal with a couple, like one extra step that we didn't do before in a one-way between. So the good news is these essentially stay the same. Right? So between groups, within groups, total, are all the same whether you're doing a one-way between or one-way repeated measures. They're exactly the same. There's no difference. So we're still going to find these three things the same way we did before. That's really good news. Those things are not new. They're done the same way. So if you have them down, or once you get them down from a one-way between groups ANOVA, they're the same here. Nothing's changed. All we have to do is do one extra little bit, which is this right here, sum of squares for subject. This is the one extra piece that we need to find in a repeated measures that makes it a little bit different than a one-way between groups. So these are the same. One additional thing we got to find, and then we're going to use that to find this error. Okay, so the total is still the sum of squared differences of all scores around the grand mean. Same as it was for between groups. The between groups mean, or between groups sum of squares, in this case, group is defined by the time, right? Pre, post, follow-up. So it's not group in the same sense, but we're going to treat it the same way. So the differences across time is each mean for each time, the mean of pre, the mean of post, the mean of follow-up, all around the grand mean, just like before. The within groups is just all the scores around their own group mean. That's exactly the same, nothing's changed. Then we get this S, which is the subject means from the grand mean. This represents, like I said before, this represents where subjects sort of remain consistent. This is the consistent differences between people. Right? So how do people sort of score consistently? Are they consistently really high relative to other people? No pun intended. Are they consistently really low relative to other people in the group? So it's this consistency, consistency is not random. So we're gonna find the consistent scoring people have and remove it from the within groups, the typical within groups we did before. And what's left is going to be the random part, differences between within groups and subject. So we're going to find the consistent part of the within groups. We're going to remove it, pull it out. And what's left over is going to be the truly random part of within groups. So it's going to be the parts of each, like pre and post and follow-up, where people weren't perfectly consistent. So it may be that on average, one person is really, really high all the time or really, really low. But you look at individual time periods, they may sort of flip-flop around a little bit. Sometimes they're a little bit higher than others, sometimes they're a little lower than others. And there's some, some shuffling around of people's scores. And that's actually really the random components, where their consistent parts measured by their subject averages is not really random anymore, and we can't use it. This actually is, it may sound like it's a pain in the butt because it's extra things, but this is actually what makes repeated measures really good. Right? This is actually the benefit of doing repeated measures, because we're able to take a portion of variance that we would have if this were independent or between groups, that we would have treated as error, and we're removing it, which means that our error term is going to be smaller. When our error term is smaller, remember that our f is going to be, at some point we're going to talk about f being our mean square between groups still, so it's like it was before, over our mean square for this new error. And because this is smaller than the previous, mean square within groups, it's going to make our f bigger. We're going to have a more powerful f-test because we're able to minimize the error by removing this consistent part out. All right, so we can see how what the individual differences are that are consistent across people. Identify that variability, remove it, get a smaller error term, and a larger f. That's great. This is why repeated measures of ANOVAs are nice. They actually allow us to, one, use less subjects because they just are repeating, and two, have the potential for a larger, more powerful f by being able to identify the consistent between subjects variability and remove it. So we get a smaller error because we're going to take our within groups, remove that consistency out that we call S, the variability for subject, and get a smaller error term. So another way of sort of breaking this down is that total, just like before, total equals between plus within. Here's my within right here. Okay. It's just we're going to take our within and we're going to break it up into the sum of squares due to individual differences, consistent differences between the subjects, and then the random part that is left over in the sum of squares for error. So let's think about how the variability is sort of being broken down. So I mentioned it in the last slide, but let's think about it, because we did this for the factorial, so I want to sort of put the factorial and repeat it sort of side by side. So in a factorial between groups, everything starts off as we got the sum of squares for total, okay? Right, that's every subject around the grand mean. Those two end up being the same, okay? And when looking at it, they're all broken down in the same way by looking at the sum of squares between groups and the sum of squares within groups. Those are also the same across the two. Okay? So far, no different. Sum of squares between groups and sum of squares within groups. Okay, those are the same. And this is at the sort of level of, once you get to the level of a sort of one way between groups, right? It's the same. If you treat it sort of a one-way between groups, we're really just looking at between versus within groups, and that's it. Where things start to differ is that on one side, for factorial between groups, we took and separated this out into the sum of squares for A, the sum of squares for B, and the sum of squares for the interaction between A and B. Right? So we took our between groups and separated our between groups into multiple components of variance. So there was, in a one way, we assume there's just one way that groups differ. So we just call that sum of squares between groups. That's it. There's just one way that groups differ. So that's it. When we do a factorial, we have at least, at least two IVs. Well, the groups differ from each other along the A dimension. They differ separately along the B dimension. And then sometimes A and B works together to affect the means even more or in a different way than A and B, individually, and we get this interaction. These are all different ways in which our groups differ, so they're all components underneath the between groups sum of squares. So and that's what we've already talked about. This is not new. This is all part of the factorial between groups part, right? So I'm actually going to I'll draw a line here. So, again, so here, like, this is like where one way between groups is, and how we sort of take our one way. Sorry about the noise. This marker's getting noisy. It's probably dead or dying. Making a lot of racket. So, you know, at that level, you know, factorial and repeated and one way are all sort of the same. Where factorial differs is that it further separates out between groups into these components. All right, well, how does repeated measures differ? With repeated measures, we're going to leave between groups alone. This actually stays the same. It's no different. One way between groups, one way repeated, between groups is calculated the same way. What does happen is that we're going to break the sum of squares within groups down into two parts. There's going to be the sum of squares for subject and the sum of squares for error. This is the consistent differences between people. This is the random differences between people. All right, so we're sort of starting to separate out into the parts that are consistent differences, consistent individual differences, versus our random differences. And we're going to break those down to these two different effects. One for the subject, sum of squares for subject S, and then the other one we're going to call error. Sum of squares for errors because it's random. Up here, you know, at the level of one way between groups, within groups and error are synonymous. They're really the same thing. We're treating our within groups as our error, as random variation. So they're sort of synonymous. But in repeated measures, we're actually splitting up the parts that are consistent between differences between people and the parts that are inconsistent or random. So all of a sudden, within groups and error are no longer the same thing and no longer synonymous when it comes to repeated measures. We're actually creating a separate error that we're going to use for our F that's different than it is in a between groups. But we're leaving between groups, the sum of squares between groups, completely alone. It's actually staying exactly the same as it is in a one way between groups. And some of these markers I think are getting dry or something. It's not writing up as bold as they used to. Okay. Between groups gets left alone, it's the same. Within groups is now being split into subject and error. And this is the one that we're going to use. This is the thing that we want. We actually are looking for this thing when it comes to our F test. We'll get to that in a second. So I wanted to compare this because in a factorial between groups, the within groups is actually left alone. We leave this alone and we're splitting out the between into multiple components. The other side, repeated measures, the between groups is being left alone and it's being done the same way as it is in a one way between groups, right? It's the within groups that are now being split. So just like with one way and factorial, we sort of stepped through the different components of the sum of squares because they all add up to total. So total is between plus subject plus error. We can talk about each of the components. Now I didn't do all the triple sum stuff here, sort of simplify things down a little bit because we are summing over individuals in each group, so it really should be two sums, but I just sort of simplified it. We're looking at the sum of squares total. This is sum of squares between groups. This is sum of squares subject. And inside here is sum of squares for error. So let's talk about those pieces and how they work. So the first part, again, is Yij. So I'm taking every individual in every group. So we have our groups here synonymous with time. So I'm taking every subject score in each of the times. So subject 1 in pre versus the grand mean. Subject 2 in pre versus the grand mean. Subject 4 in post versus the grand mean. Every single score in every single time around the grand mean, which means I'm doing this 30 times. Because I have 30 scores. Okay? 30 scores around the grand mean, each time squaring, adding them all up. Here, I'm taking the M sub j, which means the mean of each group. So the mean of pre, the mean of post, the mean of follow-up. Each of those three means around the grand mean squared. And I'm going to multiply by the number of subjects that are in each of those groups. So this is exactly the same as it was before as the sum of squares between groups. So again, this lines up perfectly. This is the sum of squares for total. This is exactly as it has been, sum of squares for between groups. No different whether it's a between groups ANOVA or repeated measures. We're going to calculate the sum of squares between groups the same way. It has not changed. Now, this is where it's important to keep track of subscripts. So here, this is M sub j, where j is a stand-in for each of the group means. So the mean of group 1, mean of group 2, mean of group 3. Here's something we have not seen before, M sub I. So this thing here, because this is M sub I, this is the mean, something we haven't seen before, the mean of each individual. So this is our subject means. Okay, and that's new. It's something we have not seen in any of these equations because we normally don't take the means of each subject. Why? Because subjects usually only have one score. You can't average out scores for a subject if they only have one score. Now all of a sudden they have three. They have one for pre, one for post, one for follow-up. I can take those three scores and I can create a subject mean, or an individual mean for each person. So I'm going to take each of those subject means and I'm going to subtract the grand mean. I'm going to square it. Now instead of, like here, where because we're taking the number of participants in each group is n sub j, and I'm taking the mean minus the grand mean, so I'm weighting it by n, by the number of subjects. Here I'm weighting it by group, because it took three groups, three scores across the three groups to create this mean for the subject, right? It took subject 1's pre-score, their post-score, and their follow-up score. That's three scores, one for each group, that I had to average together to get this, the first person's mean, which is why I'm weighting this whole thing by the number of groups. Now I could have used K there, I could have used anything that I wanted there to represent number of groups. I just used G because, you know, the word group starts with G. Does it make sense? So I'm taking the number of groups and I'm going to multiply that. Once I sort of subtract the grand mean and square each time, I'm going to take it and multiply by G to get my sum of squares for subject. So this is my consistent differences between subjects, sum of squares, subject, sum of squares for S. Okay, so now I have the parentheses. Now in factorial ANOVA, the parentheses actually represented an interaction. Right? It was, we took the sum of squares between groups, minus A, minus B, and got the sum of squares interaction. So I want to point out here that the brackets here also represent interaction, even though I haven't talked about it that way. The sum of squares for error is actually an interaction between the groups and subjects. So sometimes in a repeated measures, the SS for error, you may see it as written out as the sum of squares for A by S, or sometimes as the sum of squares literally A by S, because it actually is an interaction between time, pre, post, follow-up, and subjects. It's how subjects differ from each other in a way that is different across the groups. It's the inconsistent scoring. So this does parallel the brackets in the factorial ANOVA, and that it is an interaction. It's just a strange interaction. It's an interaction between people and time, which is an odd one, but it's random because it's the part we can't explain. All right, I know why someone scored relatively high, because their average was high across all the time. So even though I can't explain it, they're just better at recall, right? I can explain that. But why that person in time 2 wasn't the highest, they were the second highest, and there's some flip-flopping around, those things I can't explain. That's why we're going to treat that as random. And it's that interaction between time and subject is going to be our random error, our noise that we're going to use. So how do we find it? Let's look at this first part. This first part says I'm going to take every individual in every group, and I want to subtract from that the means of each group. I'm going to square it, and I'm going to add all that stuff up. All right, so scores around group mean. Well, this in here, this first part, is really getting to the sum of squares within groups. In a one-way between groups ANOVA, this would be our error. This would be our denominator in our, or not the sum of squares, but the mean squares would be our denominator in our f, because we're going to treat that as random. So before, remember we said that the s and error, those two components, these two things are both parts of sum of squares for within groups, right? They're both there. They're both parts of it. We're taking sum of squares within groups and splitting it into s and error. So I found s by itself here. So now I'm finding the overall within groups. So to get the sum of squares for error, I'm going to take that sum of squares within groups and subtract out that sum of squares for s we already found. So this is sum of squares for s. And again, you may be compelled to want to cancel things out. But the reason why this is here is because this sum of squares within groups contains both an s, sum of squares for s, and a sum of squares for error combined. They're both together. They're both combined in sum of squares within groups. So having the sum of squares for subject already here, if looking at the sum of squares within groups, I actually have another sum of squares for subject sitting here. I don't want two of them, so I'm going to subtract it out to get rid of it. So I only have one sum of squares for subject. And in the brackets, I have a sum of squares for error combined. So this whole thing, from here all the way to there, this whole thing combined is going to be our sum of squares for error. Right? Because there's a sum of squares for errors inside the sum of squares within groups. To find it, I'm going to subtract the other part out, the sum of squares for subject. And what's left when I subtract out is the sum of squares for error. So I got sum of squares for total, sum of squares between groups, sum of squares for s, and I got to find a sum of squares within groups. Once I find that, I can subtract the sum of squares for s I already found, and then get my sum of squares for error by itself. And then what we end up having is total equals between plus subjects plus error, or BG plus S plus error ends up being our sum of squares for total. And they all still add up. Just I've left the between groups alone and split up the within groups into the consistent differences between people and then the random variability on average between people. Okay.